All right, well, I don't know if anyone else is going to come in person, but we'll get started because we have a full day of events and lots of things to do today. It is my pleasure to introduce Jason Kawalec as he presents his senior honors thesis. I first met Jason in January of 2020, I think, right? That was when he interviewed for a summer arrestee position for me for working with drones and education. Come on in. So he was selected out of lots of candidates to be my summer researcher. We obviously know that that year did not go to plan, but we were able to pivot and complete a virtual research project that summer. And since that summer, he has stayed on and done some independent studies, various topics with me throughout the semesters. He worked with Luju for a summer. And he's done many other things, very accomplished undergrad. He taught a FIG seminar this year. He's the editor-in-chief, right? The editor-in-chief of the Arrestee Undergrad Research Journal that got some news and press this year. So he has lots of accolades to his name. And most recently, he was awarded the Chancellor's Excellence Award for Excellence in Research last night. So we got to go to a gala and dress up and we got a nice little crystal award for it. So, Jason, floor is yours.
Well, thank you, and good morning, and thank you to all of you for coming to my presentation. My talk is on my project, applying UAV facilitated photogrammetry to the dormant Barva volcano in Costa Rica. So Costa Rica is similar to many of the countries in Central America, in that it is home to a great number of volcanoes and is also one of the most seismically active regions in the world. And central to both volcanism and earthquakes in Costa Rica is the subduction of the Cocos Plate beneath the Caribbean Plate, subducting at a rate of about 9 centimeters per year near Costa Rica. And the subduction produced the present-day Central American volcanic arc, which stretches from Guatemala to southern Costa Rica, runs parallel to the Pacific shoreline, and the arc started forming the earliest near Costa Rica in the Quaternary about 600,000 years ago, and it started forming the latest in Nicaragua about 330,000 years ago. So focusing in on just the southernmost portion of the Central American volcanic arc is the Cordillera Central, which is composed of several stratovolcano complexes, including Poás, Iratsu, and Turrialba. Those are the active volcanoes in the Cordillera Central. And it's important to note that they are directly above the Meseta Central, or Costa Rica's Central Valley, which is home to about 65% of the population of Costa Rica, as well as the capital, San Jose. And Poás and Turrialba last erupted in 2022, so last year, whereas Iratsu last erupted in 1977. And in contrast to those volcanoes, Barva is dormant. We've dated its last eruption to about 8,000 years ago, plus or minus 2,000 years. And compared to the relatively well-studied Poás, Iratsu, and Turrialba, there's a lot that we don't know about Barva simply because there hasn't been a need to study it. It's inactive. There's an extensive vegetation on especially its northern flank. So it's not as well studied in literature as Poás, Iratsu, and Turrialba are. But I believe that it would be a significant threat. It would pose a significant threat to the Central Valley, given how close it is, 23 kilometers from the capital. And it would pose a significant threat to the population, the industry, and agricultural centers on its southern flank. And I believe we can say that because Costa Rica's Central Valley certainly exists in the shadow of Barva, and that you can see the extent to which Barva has influenced the topography of central Costa Rica. The red shows the exact outline of how far Barva's lava flows have reached in central Costa Rica. And most of this is due to an eruption in 322,000 years ago that produced the Tirbi Formation, or the Tirbi Tuff. That was a very large pyroclastic event emerging from the Barva caldera, and actually resulted in the collapse of the Barva caldera. that reached 40 kilometers within the Central Valley, as well as depositing up to 80 kilometers of volcanic material, in some places closer to the summit. And this event is attributed to Barva from a series of multiple pulse eruptions from the Barva caldera. And it certainly would have devastated the Central Valley today, given the populations nearby. So here's a more detailed look into the structure and lithology of Barva. So Barva is an andesitic complex shield volcano, meaning that's mostly composed of units of lava flows, but there's also some large pyroclastic deposits. And you can see that Barva has several summit cones, as well as some parasitic cones. We'll be investigating that in the study. And parasitic cones are essentially just cones that are not attached to the central vent of the volcano, but are still part of that volcano. In terms of the lithology, petrographic studies on Barva have shown that the lava flows are primarily andesitic pyroxenes and basaltic andesites, as well as some olivine basalts and dacites. So the takeaway from that is just that Barva has had several different eruptive styles. It's hard to constrain exactly what its eruptive history is, because a lot of its eruptions have been so varied, from very explosive to very effusive. And also important to note that here's the Turvey formation, and we've constrained pretty well some of the neo-Barva, the more recent lava flows, like the Los Angeles lava flow and the Los Bambinos member, but it would be difficult to date any more recent layers than that, because Costa Rica, as we know, is a tropical country. It has tropical weathering, meaning that any exposed outcrops would be pretty much intensely weathered and turned to soil. And we saw that when we went to some of the road cuts in Costa Rica, so it was difficult to actually see any outcrops that weren't just soil. So given the gaps in our understanding of Barva in terms of its eruptive history and morphology, as well as the importance in understanding Barva if it were to reactivate, our study aims to assist in our understanding of Barva by constraining the morphology of some potential volcanic features on Barva's southwest flank. And the goal is that the information we would obtain from this mapping would inform future targeted fieldwork and eventual geochemical sampling at Barva for volcanic hazard assessment. So this study here, this is from a study analyzing LiDAR that was directed at the slopes directly south of Barva. And you can see that they grouped some lava flows separated by color here, directly south of Barva. And I believe that the takeaway from this is just that LiDAR can be very useful in terms of detecting lava flows and understanding their morphology. But it is expensive to implement, and we decided to use aerial photogrammetry instead, a much more cost-effective method to basically still understand the topography of a region by studying it with a drone. So that's where we directed our study, to Area 1 and Area 2, just over here. And we had the help of Dr. Paulo Ruiz from the University of Costa Rica in identifying some interesting features over here, which he suspects are parasitic cones. So these features are Mystic Pasture, Monte de la Cruz, and Rancho del Nitere. And he believes that these are potential parasitic cones. Monte de la Cruz is one that is a little more well-researched because it has been attributed to the Los Angeles lava flow. So we do very highly believe that it is a parasitic cone of Barva. But these other cones, Mystic Pasture and Rancho del Nitere, have not been understood in the context of volcanology, and we simply named them those names because there is no established names for those cones. We just named them by the farms that they were located on. And here's the summit. Here you can see the outline of the caldera. So as I said, our methodology was aerial photogrammetry, which refers to the use of an aircraft, such as an unmanned aerial vehicle or a drone, to essentially fly over a region, take pictures, and then we can use those images to develop a three-dimensional model of that region. So in last July, Dr. Ruiz, Dr. Adamo, fellow undergrad Mike Pinella, and graduate student Ria Sarkar, we went to these sites in Costa Rica, and we flew the drone over each of these sites and took a lot of pictures. So our drone was a DJI Mavic 2 Pro. We also had the DJI Mavic 2 Pro has an internal GPS system, which means that it imprints the geolocations of each image onto each image. This will be important later when I'm discussing georeferencing. And then we also had another means of georeferencing, which was using ground control points and our handheld Garmin InReach Explorer plus GPS. So the process or the procedure to collect ground control points are essentially just features that you know the geographic coordinates of within a region, so that you can identify those features within your images and use them to anchor the model that you create to a real world coordinate system, or like ground truth, that you could say. So we did that at each of these sites. Here's an example of just a flag that we used as a GCP. And then also you can use black and white targets. And we completed 2 flights, 2 90-meter altitude flights at each site. The first flight being at 90 degrees, camera angle at 90 degrees, and the second flight at a camera angle of 45 degrees. And we compiled 386 images for Mystic Pasture, 556 images for Monte de la Cruz, and 960 images for Rancho Doña Tere. The reason for having much more images at Rancho Doña Tere was we were dealing with a lot of high winds and cloud cover at Rancho Doña Tere, so we had to halt some flights midway through and then come back the next day. So the procedure, once you acquire your images, is to use a structure from motion program to actually develop the models. So this pretty much outlines the way that structure from motion programs work. It operates on the traditional principle of stereoscopic photogrammetry, in that you can derive three-dimensional measurements of an object or a scene based on two-dimensional images of that object or scene. And the structure from motion program will essentially identify any matching feature points between these closely overlapping images to reconstruct the scene geometry and the camera positions. So the structure from motion program we used was Isosoft Metashape, and the procedure is to go from your images to a sparse point cloud. Those are the matching tie points. Then you use that sparse point cloud to develop a dense point cloud, which extrapolates all the points from the sparse point cloud. And then the products that you actually want to look at and analyze are the digital elevation model, the orthomosaic, and the textured 3D model. The digital elevation model is essentially just the surface of the scene that you have with all the elevation values stored into each coordinate. And then the orthomosaic is all the pictures stitched together onto the surface of the DEM. And textured 3D model is mainly just for visually seeing the 3D structure of the scene. So I wanted to run through the procedure to develop these models, starting with the sparse point cloud. You can see here, this is the camera positions overlaid onto the sparse point cloud. Each camera position is a blue square, and you can see just pretty much the flight path grid that our UAV took. We took it over the center of the cone. That's why there's a lot more confidence in the region directly over top the cone. And then once you have the sparse point cloud, you can extrapolate millions of points from the sparse point cloud into the dense point cloud. On the left here is the dense point cloud shown in a confidence filter, meaning that the points in red are where the program is least confident in constraining the position of those points in the land, and the points in blue are where the program is most confident. So process here is just to remove those low confidence points, as well as any extraneous parts of the model that you're not going to be looking at. That leads us to this dense point cloud on the right. And then finally, you can develop the textured 3D model. This is the textured 3D model for Rancho Donatore. You can see the general rise of the cone compared to the surroundings. You can also see some details if you look closer, like just the anthropogenic features, the buildings. But the actual products that we were interested in analyzing are the digital elevation model and the orthomosaic. So we developed a digital elevation model and an orthomosaic for each of the 3 cones. This is the digital elevation model for Rancho Donatore, which is the furthest from the summit. And we saw about like 50 meters of relief. We resolved it at 9.5 centimeters per pixel. And this is this cone has an area of about 70,000 meters squared. Same thing for Monte de la Cruz. We resolved it at 10 centimeters per pixel. So about 50 meters of relief from the bottom of the cone to the top of the cone. And this was the largest of the 3 cones that we looked at, with an area of 100,000 meters squared. And is also closer than Rancho Donatore, but further than Mystic Pasture from the summit. And then this is the Mystic Pasture cone, showing 40 meters of relief. This was the smallest cone at an area of 40,000 meters squared. And we resolved this one at 4.5 centimeters per pixel. So this is also a textured 3D model of Monte de la Cruz, just showing there is one of the crater lagoons, as well as there. You can see just the how the tree line pretty much encompasses the cone itself. So another, as I said before, we also had a different georeferencing method. So we wanted to compare if this other georeferencing method, the handheld GPS and the GCPs could produce similarly accurate results in terms of measuring the elevations. So all the models I just showed you were georeferenced using the internal drone global navigation satellite system. And the procedure to develop these GPS georeferenced digital elevation models is very similar, as I just laid out before, but the difference is that you disable the geolocations imprinted by the drone, and you instead identify the ground control points across the images and use that to georeference the models. The idea is that we could do a comparison analysis between the elevation data from the internal drone global navigation system to the handheld GPS. So the way that this is done is that within ArcGIS, you can use the spatial analyst raster calculator to essentially calculate the difference between in the elevation values between UAV and GPS georeferenced DEMs. And then if you run the standard deviation and that resulting data set of the difference in elevation, then you get the root mean square error. Here's the equation, and that just essentially represents the average difference in elevation between models. So we did that for Mystic Pasture and Rancho Donatore. Unfortunately, we couldn't do it for Monte de la Cruz because we didn't have the resources to place and measure ground control points at Monte de la Cruz. But in Mystic Pasture, we saw an average difference in elevation between the models of about 20 meters, and then a pretty similar one at 17 meters for Rancho Donatore. So given that we're seeing relief of about 50 meters, this does seem pretty significant for in terms of the elevations produced by these 2 different georeferencing methods. So our interpretation of why these methods seem to produce such different results can sort of be shown here. We think it's due to just the uneven distribution of ground control points that we had. And that's principally due to the fact that we couldn't access a lot of the terrain. This was all private farmland. Here's the cone itself covered in trees. So there was just a road here that we could place ground control points on. And you can see this is the comparison of elevations visualized in ArcGIS, showing how near the GCPs, it's the models, the UAV georeferenced DM and the GPS georeferenced DM are the closest and the most similar in elevation, whereas further away, there's a lot of difference up to negative 98 meters, showing that the GPS georeference DM predicted much lower elevations for this part of the area compared to the UAV georeference DMs. So the takeaway from this is just that the UAV georeference DMs that we developed seem to be much more vertically accurate compared to the handheld GPS georeference DEMs. So we also want to do the same comparison analysis procedure, comparing basically to quantify how accurate our results are compared to the previous highest resolution data set. So this is the regional digital elevation model, and it's at about 10 meters per pixel, and it's taken from aerial photographs taken in 2007 of Costa Rica. And you can see our sites here, and these are then blown up on the side, and they're visualizing the elevation difference between the DEMs that we constructed, the UAV georeference DEMs, and the topography. So you can see that the flat sections here, those align most well with the regional digital elevation model, whereas the actual cones themselves seem to show the most difference in elevation. They show much higher elevation in our models compared to the regional elevation models. So we interpret this as our models showing improved elevation measurements on the compared to the regional DEM. And this makes sense because the regional DEM is much lower resolution. It only resolved, for example, 16 elevation measurements for the Mystic Pasture cone, whereas we were able to resolve 183,000 elevation measurements. So we were able to see much smaller scale changes in height that the previous regional digital elevation model just couldn't see from the resolution it was at. This is a table of the average differences in elevation between the digital elevation models that we generated and the regional digital elevation model. And then once again, this takeaway that you see almost 20 meters of average difference in elevation between the GPS georeference DEMs and the regional topography. Whereas between our models and the regional topography, there's about, on average, 7 to 9 meters of difference. So we consider this as meaning that our models were able to resolve, much smaller scale changes in elevation that the previous topographic data could not resolve for these cones. And there is also an added influence of the trees adding a small amount of extra height to our digital elevation model that may not have been accounted for in the topographic data that we compared it to. Another aspect of the study to mention is just that when you plot these cones onto this regional digital elevation model, you can see that they seem to align along 19 degrees west of north. And this sort of stretches to the summit of Barva, as well as connecting some other possible parasitic cones here and here. And this was first hypothesized by Rojas et al. 2017. And they also just looked at this topographic data and considered that these cones may align because of a potential volcanic tectonic fracture, meaning that these cones had a similar origin produced by a fissure from the summit. So this is something to consider when we return and examine other potential cones that may lie along this fracture, specifically this cone and this cone. So in terms of conclusions, in the study, we constructed digital elevation models for 3 unexplored parasitic cones of Barva at higher resolutions than any previously constructed, meaning that we were able to resolve the elevation at a much higher resolution of these cones. And there's also the conclusion that UAV facilitated photogrammetry can produce high resolution, vertically accurate digital elevation models of large areas up to 100,000 meters squared, even without the use of an RTK. An RTK is a real-time kinematic unit. It's essentially just a higher accuracy form of GPS technology. So what our next steps hope to be is this is a figure from Mike Pinella showing some work being done to use AI, or the specifically the random forest algorithm, to differentiate the trees from the topography. So the green, the trees, the brown is the topography, and then the red is some of the crater regions. And the idea is that if we have some of the surface level of the cone next to the trees, we can generate an average height of the trees and then remove those to constrain the actual elevation of the cone itself. So that's one of the next steps. And then we also hope to return to Costa Rica this summer with an RTK to have much more certainty over the accuracy for flights at other potential cones along the fracture that I showed you, as well as some cones at the summit. These are my references. I would like to acknowledge Dr. Adamo for being just the most supportive advisor I could have found here at Rutgers, as well as the Rutgers Global for funding this research, the Rutgers Sparks grant in this department. Thank you to all of you for coming. Thank you to my family and friends for supporting me. And yeah, I hope you enjoyed, and I will take questions.
Online clocking too, so.
Yeah.
Very cool. So you can see what looks like potential cones on that line.
Mhm.
So do you think, is it reasonable to assume that they are cones, and can you actually look between the cones to see if there's evidence of some sort of ground displacement that could be related to the actual cause of the cones being where they are?
I think that would be a really interesting for us to when we go back to look at, because it wasn't until we came back and looked at the topographic data that you could see this this line between them. So yeah, I think it would be interesting to see if there's any ground displacement between the cones. Obviously, the difficulty with that would be a lot of this is private property, a lot of it's covered by vegetation and tree cover. But yeah, definitely. And in terms of what other outcomes could have produced these cones, I don't think there's much else to conclude than that it could be parasitic cones. Yeah, sure.
Yeah, I noticed that the cones are sort of in a line, but that line is also parallel and close to the contact between much older stuff and younger stuff. So it could be that magma was coming up along contact between those two formations and then just popping out. So it might not actually be a fault. So I think you should have a second hypothesis.
Okay.
Yeah, I was just wondering, the first question, first of all, great talk. Do you see any other cones towards the north of the volcano
Yes.
that aligns with that?
That aligns with this fracture. I don't think so. I don't have this blown up, but
Okay.
when I've looked at it, I don't remember like seeing any further along this fracture to the north of the summit.
North of the summit, there is a line.
There is further up here.
Yeah, so they're off your map.
Okay. Yeah, so I guess that is something to.
It's
Yeah.
probably worth to look at.
Yeah, yeah.
And then the second question is that when I saw your DM, there was like a void areas there.
Yeah, those are just sorry, go ahead.
Yeah, so what happened there? And then can your software extrapolate between?
It can, but we disabled like interpolation. So well, this is the difference. That's why there's a lot of the void gaps here.
Yeah,
because
so this is the.
yeah. And then going back to just the DMs.
Yeah, so. Like,
Yeah, in this model, there's some gaps, and that's just because I disabled interpolation of these digital elevation models. I wanted to make sure that all the elevation values that we had were strictly calculated by the program and not just interpolating between elevation. Like I could resolve, I could just use the interpolation to resolve those elevations, but it wouldn't be as precise as these elevation values, which are strictly constrained from the actual, photogrammetric procedure.
The other reason is because, the picture you showed with the blue frames, that the flight paths were only directly over the stuff. And so the reason why we're getting all around it is because the drone and the pictures are good enough to get, it kind of, when the camera's at an angle, we just kind of pick up the side areas. So you don't have as many pictures that are in the, covering those areas too.
So your field of view is about 70 degrees and you're using a 45-degree parallax, right? So your center is going to be very well aligned, but the outskirts are going to be so much more distorted, and that's one of the reasons that you have lots of like good fidelity when you do this RMS comparison. But that being said, now if you go back to, if you go to your slide where you're comparing the resolution of your TDM to the original TDM.
Yeah.
So here, can you walk me through how exactly you're making this comparison? Or you could, I mean, there are two radically different resolutions, right? So are you
Yeah.
downgrading one or upgrading one?
Downgrading our digital elevation models.
So then you have few pixels.
Yeah, you have very few pixels to
Yeah,
compare them
so,
to.
I mean, yeah, if you have few pixels, I wouldn't put a lot of weight on the
Yeah.
RMS stuff anyways, but I think one of the ways to combat this would be to, unless there's a reason you're using a 45-degree parallax, and you probably have higher number of images with lower parallax and get much more, much less error when you do rectification. The other thing that I wanted to ask you was when you were comparing the GPS, handheld GPS, to your DEM that you made.
Yeah.
With the, are you making sure that the equity potential on both of the altitude measurements are the same? In other words, what is the really in comparison to? Because the GPS is very compared to the potential of the Earth, whatever that might be in the setting, but what is your reference point?
Do you mean like the horizontal accuracy?
No. So what do you compare? The
Oh, okay. Oh, so yeah, pretty much the base map on ArcGIS, just to confirm that they are horizontally aligned.
But yeah, you probably want to double make sure that in GPS is also the same. A
Mhm.
lot of times they're just the geo,
Yeah.
which might be different at different places. If they're using like a whole world geo, they're going to have much higher inaccuracies. But yeah, great work.
We would love to talk to you more. because
Yeah,
this
I'm
is
sure
the,
she has a lot to say about
This is
this.
a capstone project, so I'm officially inviting you to be on the committee. Any questions online?
But, how come you didn't use the RTK first year? It just wasn't available?
We didn't have it.
Okay, that's all.
We only had one, so it's John's, but
We
with
built two
grant,
more.
yeah, so now, because I bought the other stuff, so yeah, we're gonna bring it back. I mean, so last summer was really just a proof of concept site survey to figure out, and now this summer will be much more targeted of looking for things.
How tall are the trees?
We were actually, yeah, we were talking about this last
There's
week.
something that's gonna happen.
Really tall down there, don't they?
Yeah,
We do.
it was the
Like
average.
200 feet something.
The average was about 20
20
meters,
meters, yeah.
so anywhere from 10 to 25 meters was
Yeah.
the average.
Wait, the tree is 1 meter?
Yeah.
Some of them, yeah.
Jesus.
Yeah, these are big, big trees.
I told you. You
Yeah.
need to look at how the trees were.
So if this is the proof of concept, and it looks like you can do this.
Yeah.
But there are little tiny spots compared to the size of the volcano.
Right, yeah.
That's probably maybe the best you can do around here, doing all the cloud cover. too.
Yeah.
Because you're right at the convergence between the Caribbean air and the
We struggled with
air.
that a
It's
lot.
always cloudy.
Yes,
It went to the summit and it was just too cloudy to even fly.
yeah, the thing is, we're gonna have to get up like 2 in the morning and be on the summit at like 6 or 7 AM after you hike up to the top to avoid that. But yeah, we definitely had more than a handful of hike,
Yeah,
can't do anything.
lost days.
Yes.
So is there, given how small the spots are, is there geologic problems that are more appropriately looked at with the spots? I don't actually think faults are gonna work very well because of the soil. I mean, the soil development is massive. I
Yes.
think the fault trace is gonna be wiped out unless they're, like last year, which they aren't.
No, it's very weathered.
Yeah.
We couldn't even tell what the cones were made out of from the points that we could see because they were just so highly
Well, they're
weathered.
made out of red mud.
Yes. Pablo thinks that they are ash and that made of ash or a combination, but that's another thing we're trying to find some other places to look at.
Yeah, you need another generation of development before they dig into the cone because they need the cinders for them.
Yes.
So,
Yes.
going to the caldera, is the shape of it telling us about the last eruption, or is that also just the way the water drains, the rainfall? Looks like it drains to the northeast primarily.
Yes.
Is that endemic of the eruption, or is that just because most of the rain falls and has eroded that much out?
I would say yes to both, and that I think it's partially constrained by the eruption from 322,000 years ago. But I also think a lot of it is produced by weathering and erosion from.
That's the height across the continental divide,
Right.
so,
Rainfall is highly asymmetric.
yeah.
It's an excellent thing to try and figure out. So
So Barry, you asked a question about, yeah, so he asked about like cones closer to the summit. I mean, that's what Pablo studies is on the landslides in the area, right? So it could be, there might have been something, but maybe it's wiped away, but that's something we can, Pablo's online listening, so.
Oh, okay.
So much more to do this summer.
But there is a well-developed line of cones that you can see from the road. And they think gave rise to the lavas at about 200 to 300,000 years old. So they would help to tie down the structure.
Yeah.
That's a great news.
Yes.
Great job, by the way. Going back to the last slide.
Yeah.
So would it be beneficial in any way to tie your elevation models to the GPS? Because it seems like there's a pattern here. And that could just be, right? It seems like it's not a fixed error from the GPS, but it does seem like it follows some sort of trend. Would it be worth it to try to model that and tie your data to the GPS data, or do you think?
You mean combine the ground control points with the UAV
Sure, yeah.
internal geofencing system, or?
I mean, I guess, so here, you're showing the difference between what the UAV is saying and the GPS handheld units, right?
Yes, yeah, those the models produced by those separate methods, yeah.
Sure. So is there any value in, trying to tie the GPS coordinates into it, or do you think they're just completely inaccurate compared to the UAV?
But when I combined them, because I initially had both the GCPs and the UAV geofencing system enabled, it actually came out with the result that was like pretty much in between, like it was still predicting like very low elevations over here. So it seemed to favor the GCPs in terms of georeferencing the model. So it did still lead to some clear inaccuracies in terms of the georeferencing. I do think that if we had an even distribution of ground control points, which was once again difficult for this site, but if we did that with an RTK, I think we would see much better improvement. We would be able to use those the RTK georeferenced models instead of the internal GPS georeferencing models.
Sure.
So,
Yeah.
So all photogrammetry gives you is relative. Right?
Yes.
It doesn't give you elevation at all.
Yeah,
It just gives you relief. So you have to tie to some sort of GPS control.
Yes.
So what GPS control are you using to tie the relative relief to?
Do you mean
Eternal.
yeah, the drone internal, which is
Okay.
Yeah.
The drones, yeah, okay. So I guess, yeah, you're working at what, 1 centimeter per pixel or 10 centimeter per pixel resolution. And I'm just wondering, is the juice worth the squeeze in other way? I mean, in other words, like, do you really need that resolution? What are you hoping to answer with that resolution?
I guess smaller scale changes in the elevation of the cone, but yeah, it's something worth considering if
Yeah.
sacrificing the resolution is better for
Yeah, I mean, we don't need it super high if we're not measuring, because we're not looking for yearly changes like on a beach or something, so you're right. For us, just figuring out the topography, the resolution, we have to do those specific.
Yeah,
So,
I mean, yeah, you don't have that in terms of resolution, before you will get much better control.
Mhm.
Just can do this with 1 meter pixel.
yeah, still better than what's out there, right?
So your spatial is 10 centimeters by 10 centimeters, what's your vertical? Error? Or
What do you mean the vertical error
what
from?
can you resolve with this? Can you resolve
That
that?
would be probably about 10 meters. I think,
10
vertical
meters?
resolution. Or-
So the thing that
Yeah,
the
with
Johnson,
Johnson,
oh,
yeah.
you said 5 meters vertical for the conservatively for the drone.
We'll
The
be able-
solution is right.
Yeah,
If you're looking at this and you can only see it's from here to the ceiling or above.
Oh, thank you, Jason.
And then I got a poster, presenters are gonna